that molecules are normally saved in some format, such as Cartesian coordinates, which give the positions of atoms in three-dimensional Cartesian space in terms of angstroms. So there's a lot you can do with that. You can determine the distance between atoms. You can determine what kind of bond is between that. And the visualization takes that information and puts it in a format that we can readily visualize. Okay. And I hope as you were constructing models that you are certainly asking particular questions like, is the stereochemistry correct, R or S, when you draw? That's going to be very important, because if you get the stereochemistry wrong for a ligand that's supposed to bind to a receptor, a protein receptor, if that stereochemistry is wrong, your binding is not going to be as good, or it might be better. It certainly won't be the correct, you won't get a correct binding energy if you've got the stereochemistry incorrect. The other most important thing here that people tend to forget is, are all atoms present? And that question, really, the most common issue is people forget to include hydrogen atoms. And when we do electronic structure calculations, omitting a hydrogen atom is disastrous, because you're omitting the electron that comes with that hydrogen atom. So it's really very important to make sure all atoms are correct. There's some questions here that are not so important, like, is the confirmation a reasonable one? So we're going to be performing a docking procedure, and the docking itself searches confirmation. So if you start with a slightly different confirmation, you're not stuck with that. It will change confirmations to try and make it fit the active site. But if you are trying to do some accurate geometry optimizations for some other aspect of chemistry, starting with a bad geometry is probably disastrous for you. So you might need to do a conformational search. Fortunately, within MarvinSketch, we have the option to do a conformational search, so it can get it to us. Okay. And I hope you're starting to become a little bit more familiar with how MarvinSketch works. It's quite powerful, actually, with power that's not often found in other small programs. And what I really like about it is its ability to search for tautomers, and its ability to search for conformations. So it's really is powerful. So please, that one of those compounds that I've given you on the handout, I've given you the wrong tautomer, and of course MarvinSketch can find the correct tautomer of that. And that's really important if we're going to try and bind it to receptor, because yes, maybe the lesser tautomer might be the better binder, but it's certainly important that we try and bind the predominant tautomer to the receptor. Okay, and of course we can do a conformational search. And of course, when you do a conformational search in MarvinSketch, you can get it. You can ask it to only produce one conformation, the best conformation. If you're interested in conformers, if you've got a big interest in conformers like I have, you can ask it to find many conformers. And here's a situation where I've asked it to find lots of conformers, and it has done so. But in most cases, you'll just want the best one. So you'll click and say, only return the lowest energy conformer, and it will provide it to you. Okay. And of course, we're familiar with isomers. Please, these are very important. Certainly, stereoisomers are very important. We've got to get the right stereochemistry. I know that if you're working with NMR, enantiomers aren't an issue. You're going to get the same NMR spectra. But when you start to look at interactions of molecules, that's the stereoisomers are really important. Of course, if you don't know what the stereoisomers are, you might need to explore all possibilities. Say, for instance, Hello? A question? Okay. Please, I can't hear that. I'm going to I just need to find my chat. There's, and in the chat, please, my chat is open. So if you've got a question, please immediately put in the chat. Okay. So if you don't know the stereoisomer you've got, or if you've got a racemic mixture, for instance, you might need to explore all stereoisomers to see if any one of them is going to be interacting in the way you want it to. And MarvinSketch allows you to search to generate all possible stereoisomers. So it's extremely powerful. So you could start with a molecule with several centers and end up with thousands and thousands of possibilities. And so if you're interested in working with thousands and thousands of possibilities, MarvinSketch can help you do that. Okay, right. I want to make you a little bit uncomfortable because one of the powerful things with working on a cluster is that if you know the right commands, you can do some incredibly good chemistry. And so certainly in the task we do today, I really want you to start to embrace the power of a cluster. That means not necessarily using MarvinSketch to create the correct file format you want. You see, you can go to MarvinSketch and you can say, please, please, MarvinSketch, save it as a PDB, and it'll do that. And you can ask it to save it as a mol2, and yes, it'll do that as well. But what if you're on the cluster and you've got the wrong format? What do you do? And of course, the cluster, on the Linux system that we log into, we have the power to change between file formats. And so please, there are lots and lots of molecule formats. And if you have a look at the left-hand side, this is what happens. I get all this list here, longer list than what you see here, probably 3-4 times this list. If I type on the cluster, if I log in there and I type Babel minus capital L formats, and you can see there are lots and lots of formats. And in it, you will see the mol2 format, which I told you is quite versatile. You'll see the PDB format, which is really, really versatile. But you'll see some other ones. You'll see XYZ, SDF, etc. Now, the program that we've got on the cluster called OpenBabel, OpenBabel is really powerful in that it can convert from any one of those formats to any other of those formats. And it takes a bit of getting used to, but what you need to do to use Babel is that you've got to type 5 words, and those 5 words must be separated by spaces. And if you type those 5 words correctly, it will convert from any file format that you want to any file format, other file format that you want. Okay, and so what are those 5 words that you type? The first one is Babel. That calls OpenBabel, and there must be a space. And then without spaces, the -I is for the input file format. And so you can see here, I'm using Babel to convert from an input mol2 file format. If the input I'm trying to convert from is a PDB, I'll type -I PDB. That's the from. And then straight after that, you have a space and you type the name of the file you're trying to convert from. So this is probably not the name of something you've constructed. I might have called it ligand1.mol2, or I could have called it hydroxyderivative.mol2. It doesn't matter as long as it exists there. You type the name of a mol2 file that's available there, and then you're ready to take that file and convert it to something else. And then you put a space on, and now you tell it what you want to convert it to. And of course, you can convert it to, for instance, a Gaussian format. Here it's output as a Gaussian format, and you type it exactly the name that you want for that Gaussian output. And Gaussian outputs normally have a .com on the end, so that's why I've written a .com on the end. And so that will convert a mul2 to a Gaussian. So those 5 words are incredibly important. The Babel, the input type, the input file name, the output type, the output file name, and Babel will convert it. And it can do many, many different formats. Of course, if you've done a conformational search in MarvinSketch and you've got 1,000 different conformers, you might want to get 1,000 different Gaussian files. And so what you will do is you'll do Babel the input and the file containing your 1,000 molecules from MarvinSketch and your output, and you'll have a -m, and you'll suddenly end up with too much work. You'll have 1,000 files created on the other side, each with a different conformation inside. So just please, I would like to try to use this. So I'm going to maybe in MarvinSketch save it as a wrong format, find myself on the cluster stuck, and so I'm going to resort to using Babel to converting from the wrong file format to the right file format, because the programs that we use in the cluster might be expecting a particular file format. They might not even like a PDB format or a mul2 format, which I said are very powerful. Okay, so just please, the file formats that I really like, what to save your molecule as. PDB or mul2 are really good for general use. So you'll find many programs that you've installed will be able to open PDB or mul2 file format. So those are really powerful. Okay, Gaussian normally has an extension .com, and so we are going to use Gaussian. So Gaussian is a really important file format that we need to work with. And there's a little program. It does semi-empirical type binding calculations, and the program's called XTB, and that XTB only takes XYZ file format as input. But XTB is an incredibly powerful program. It will do quantum mechanics optimization, approximate quantum mechanics. Well, it'll use semi-empirical type binding calculations on really large systems and calculate accurate geometries very, very quickly. So it's not as accurate as Gaussian. If you use the right methods in Gaussian, it's not quite as accurate, but it's incredibly fast and incredibly efficient. If you're interested in your work, if you've got lots of molecules, if you've got big molecules, using XTB is really important. And I want to use XTB today. So I'd like an XYZ file format today so that we can use XTB. And if you've got lots and lots of molecules and you want to save them in one file, if you've got 1,000 molecules in one file, I really recommend that you use the SDF file format for that. It's really for that. So please, those are molecule file formats. Okay. Now, it's all very well having 1,000 conformations, but they're all one molecule. What if you want 1,000 different molecules to work with? You could sit and start drawing them. I'm sure you appreciate how tough it is to really get a high quality one molecule, but to get 1,000 is difficult. So I just wanted to make you aware that there are molecule databases around, and some of them have got really good quality models in them. And one fantastic resource is Zinc, and Zinc stands for Zinc is not commercial. So the Z is for Zinc, is not commercial. And in that, on that database, it has got structures that are ready for molecular docking, for example. Okay, and simply what you do on that, if you go to Zinc, you can go in and you can search for a particular structure on it, and you can do a similarity search, and you can search all the subsets they have available, and you'll end up with a range. I think my search here has ended up with 40 different structures there. So if you are finding it really tough constructing molecules in MarvinSketch, and you've got many, you might be able to find a set or some of the molecules you need, or molecules that only need a little adjustment by going to zinc. Zinc is not the only molecular database available. There are other databases available that you can get molecules from. Okay, so you don't necessarily have to construct everything by hand. You can go on the web and you can search and you can get sets of molecules, molecular structures that you can work with. Okay, and zinc is a powerful resource for doing this. Okay. Right, so our problem in this course is we really at the end we want to do molecular docking, although we'll do some other things along the way. And I hope by now that you are able to use MarvinSketch to construct the molecule. How do you save a molecule from zinc? Okay, so I told you when you go back here is SDF if you want to save multiple molecules into one file. So if you want multiple molecules in one file, so I think that when you go to zinc, when they all come up here, you can see that little button up there. That button there is download, and it'll give you an option to download, and my recommendation is to download it as an SDF file. So when you download, search for the SDF option, and you'll end up with one thing coming down that has your 48 molecules. So if you've got 1,000, all 1,000 molecules will be in that SDF. Okay. Okay. Right. So it is possible to download those molecules for modeling. Okay. So what we want to start working on today is we would like to start doing some calculations. So I just want to tell you a little bit about, we're going to use our very little departmental cluster. This is what it looks like. So when you connect it to Carbon, here's a rack of computers. Every single one of these is a server that's more powerful than your laptop, quite a bit more powerful than your laptop in terms of computing power. And we've got a rack of them, so you can see each one of these is a separate server, and it can each one will handle some calculations that you do. Okay, one of the computers handles connections, our login details, and that's Carbon, and it's sitting down here. So when you log into Carbon, you're connecting to this computer over here. And when you copy stuff, you're copying it to that over there. But of course, we can type commands that send calculations away from Carbon to any of your other computers that are around here. So I just want you to be aware that there are two sets. I have partitioned the computers into two sets, and some of them are called batch. They're on the batch queue computers, and some of them are the Dell queue computers. Okay. I see there's a lot of errors on those computers, but they will carry on regardless. Okay, so when we submit a job to the batch queue, one of these computers will take control of a job and will do the intense calculations that you have. And when you submit it to the Dell queue, one of these computers here will take the job and will run it. Okay, and if we don't submit the job, poor old Carbon with hundreds of people logged in will have to try and do a calculation all by itself. Okay, so this is a cluster, and what's really nice is even though it's a modest cluster, the principles that we have here are the same as what you will need if you use like the Center for High Performance Computing, their cluster in Cape Town, the supercomputer in Cape Town. So the principles we use here are exactly the same as we use there. So it doesn't matter that this is a modest system. What we learn here can be used on a very extremely powerful system, such as what we have available to us in Cape Town. Okay. So I've already added you to the cluster. And so I hope that you've all able to connect. Please, if you are struggling, uh, either contact me or find a classmate who's also struggling. And then both of you come to me and contact me, and we'll have a separate session. It really helps. It really helps if you are prepared to share your screen on a Zoom session, because then I can really, what we can do is in a small group, you there, I can tell you what to do. And so you doing all the, you do the work, but I'm guiding you through. And so you're not trying to follow what I'm doing. Okay. So please, that offer is open and you must take me up on it if you're running into issues. Okay. Right. So what we did yesterday is that, sorry, that's not carbon at RU, it's carbon.ru.ac.za. Our access to the cluster is at carbon.ru.ac.za. There are two ways to access the cluster. One is through a terminal, and so we've been using PuTTY for that, and that gives us immense power over the cluster. We can submit jobs to the Dell set of computers or to the batch set of computers, and we can really cause a power drain in the data center from this very terminal. But before we do that, we need to copy files to the cluster, and so what we use is WinSCP or a file manager. So there are different ways. If you've got Mac OS, we should be able to find a way to work. And so then you can copy stuff across to the cluster. And of course, when you finish the job, you can copy stuff back. Okay. So that's how we access the cluster. Okay. And then, of course, we can ask on the cluster, we can do some calculations. So what we're going to look at is that there are two ways. So certainly in the lecture tomorrow, we're going to have a look that there are two ways to do the calculations. One is a faster way, and it's called molecular mechanics. And the other way is a much slower way, a much more intense way, but it gets more accurate results, and that uses approximate quantum mechanics to do the calculations. So we'll discuss molecular mechanics and onto quantum mechanics tomorrow, but we're actually going to use a little bit of QM quantum mechanics calculations today just to get you into how that works. Okay. And then tomorrow we'll tell you a little bit more about molecular mechanics. Okay. So at this point, we're going to take a 10-minute break. Okay. So at 9:35, please log back, and I'll work on my other computer. So I'll start up Zoom on my other computer, and we're going to try and see if we can get some calculations going on the cluster. Okay. Are there any questions? Hello? Any questions? So please, when we work, when we, okay, there are no questions, not yet. So when we go to my other computer on the cluster, I just want you to remember this picture in your mind, that we are logging onto carbon.ru.ac.za, but of course we've got the Dell computers and we've got the batch computers to work from. So please remember that, because whenever I type Dell, note that we're going to use those computers. If I ever type batch, we're going to use those computers. Okay, so I'll see you in 10 minutes time then. Okay.